In this lecture, we are going to understand how React works internally. Before learning how to build applications using React, it is important to know what happens behind the scenes whenever we create or update React applications. React has become one of the most popular JavaScript libraries because it provides a fast, efficient, and smooth user experience. Unlike traditional web applications, React does not reload the entire web page whenever there is a small change. Instead, it intelligently identifies only the parts of the page that needs to be updated and refreshes only those sections. This makes React applications much faster and more responsive. You might wonder how React is able to perform these updates so efficiently. So the answer lies in its powerful internal architecture. React uses several advanced mechanisms that work together to improve performance while reducing unnecessary processing. The first mechanism is called the virtual DOM, which is a lightweight copy of the actual web page. React first make changes in this virtual version before updating the real browser page. The second mechanism is the diffing algorithm. This algorithm compares the previous version of the virtual DOM with a new version after any changes occur. By comparing these two versions, React can quickly identify exactly what has changed. Once the differences are identified, React performs a process known as reconciliation. During reconciliation, React updates only the modified elements in the browser instead of re-rendering the entire web page. In the latest versions of React, another important feature called fiber architecture has been introduced. By the end of this lecture, you will understand how all these mechanisms like the virtual DOM, diffing algorithm, reconciliation, and fiber architecture work together to create efficient, fast, and interactive React applications. You will also gain a clear understanding of the complete life cycle of how React renders and updates the user interface whenever the application's data changes. Whenever a user interacts with a React application, many operations take place behind the scenes before the updated information appears on the screen. Although these operations happen with a fraction of a second, React follows a well organized process to ensure that the application remains fast, efficient, and responsive. Let us understand this with a simple example. Imagine a user clicks a like button on a social media application developed using React. When the button is clicked, React first detects that an event has occurred. It then updates the application's state or data based on the user's action. However, user does not immediately update the browser's web page. Instead, React creates a new version of the virtual DOM, which is a lightweight copy of the actual web page. It then compares this with a new virtual DOM with the previous version to identify exactly what has changed. This comparison is performed using a process called the diffing algorithm. Once React identifies the differences, it starts another process called reconciliation. During reconciliation, React updates only the specific elements that have changed. This efficient update process is one of the main reasons why React is widely used for modern building web applications such as social media platforms, e-commerce websites, dashboards, and real-time applications. This diagram illustrates the complete rendering process in React. First, the user performs an action such as clicking a button or submitting a form. This action changes the application's state. React then creates a new virtual DOM representing the updated user interface. Next, React compares this with the new virtual DOM representing the updated user interface. Next, React compares this new virtual DOM with the previous version using the diffing algorithm. After identifying the differences, React performs reconciliation to update only the affected elements in the real DOM. Finally, the browser displays the updated user interface. This entire process usually happens within milliseconds, providing users with a smooth experience. Before we learn about the virtual DOM, it is important to first understand the concept of the real DOM because the virtual DOM was introduced to overcome some of the limitations of the real DOM. The term DOM stands for Document Object Model. Whenever we open a web page in a browser such as Google Chrome, Microsoft Edge, or Firefox, the browser reads the HTML document and automatically creates a tree-like structure called the Document Object Model or DOM. Since this is the actual structure used by the browser to display the web page, it is known as the real DOM. In the real DOM, every HTML element becomes an individual object, also called a node. For example, elements such as headings, paragraphs, buttons, text boxes, images, links, tables, and forms all are represented as nodes in this tree structure. The HTML element is the root of the tree, followed by the head, body elements. Inside the body, all the visible elements are arranged in a parent-child relationship, forming a hierarchical structure. Whenever a user interacts with a web page or when JavaScript changes the content of an element, the browser updates the real DOM. For example, if a user clicks a button that changes the text from login to welcome, JavaScript modifies that element directly in the real DOM. Although this process is simple, it becomes a challenge in large web applications. Modern websites may contain hundreds or even thousands of HTML elements. If each user action causes the browser to repeatedly update the real DOM, the browser must perform several expensive operations. After every modification, the browser needs to recalculate the layout of the page to determine the position and size of each element. This process is called reflow. Once the layout has been recalculated, the browser redraws the affected parts of the web page. This process is called repaint. Both reflow and repaint consume processing time and system resources. When these operations occur frequently, especially in large applications with many user interactions, the application's performance may decrease. Users may notice slower response times, delays, or smooth animations. Now that we have understood the limitations of the real DOM, let us learn about one of React's most important features, the virtual DOM. The virtual DOM is one of the main reasons why React applications are fast and efficient. Instead of making changes directly to the browser's real DOM whenever data changes, React first performs all updates in a separate virtual copy called the virtual DOM. The virtual DOM is a lightweight, in memory representation of the real DOM. It is not displayed on the screen and it is not directly visible to the user. Instead, it exists only in the computer's memory and acts as a temporary workspace where React processes all changes before updating the actual web page. For example, consider an online shopping application. When the quantity of a single product changes from 1 to 2, React does not reload the entire shopping cart page. Instead, it updates only the quantity fields and the corresponding total price, while the remaining elements such as the product images, names, navigation menus, and other items remain unchanged. This intelligent approach makes React highly suitable for developing large scale applications such as social media platforms, e commerce websites, online banking systems, dashboards, and real time applications where the user interface changes frequently. In summary, the virtual DOM serves as an efficient bridge between the application's data and the browser. This comparison highlights the key differences between the real DOM and the virtual DOM. The real DOM is maintained by the browser and directly reflects the web page displayed to users. Every change affects the browser's rendering process. In contrast, the virtual DOM is managed by React. React first compares changes in memory and updates only the necessary elements in the real DOM. This selective updating significantly improves performance, especially in complex applications. Now let us see how React determines which part of the web page needs to be updated. This is accomplished using a powerful technique called the diffing algorithm. The diffing algorithm is React's comparison mechanism. Its main responsibility is to compare two versions of the virtual DOM and identify the difference between them. Instead of updating the entire web page, React carefully analyzes and what has changed and updates only those specific elements. Whenever the application state change, React creates a new virtual DOM that represents the updated user interface. At this point, React has two virtual DOM trees. The first tree represents the previous state of the application before the change. The second tree represents the new state after the change. The diffing algorithm compares these two trees node by node. A node represents any HTML element such as a heading, paragraph, button, image, input box, or list item. During this comparison, React checks whether any nodes have been added, removed, or modified. For example, if React has identified only two changes, it prepares a list containing just those updates. This list is sometimes referred to as the difference list or update list. Instead of rebuilding the complete web page, React sends only these required updates to the browser. The entire comparison process is called diffing. It allows React to avoid unnecessary work by updating only the parts of the interface that have actually changed. The diffing algorithm follows few intelligent assumptions to make the comparison process very fast. Similarly, when displaying the list of items, React uses a special property called a key. The key helps React uniquely identify each element in the list, making it easier to detect which element have been added, removed, or reordered. Using keys correctly improves both performance and accuracy during the diffing process. The biggest advantage of diffing algorithm is efficiency. Instead of performing hundreds or thousands of unnecessary updates, React updates only the elements that have been actually changed. These updates are then passed to the next stage called reconciliation, where the real DOM is finally updated with only the necessary changes. You can think of reconciliation as the execution phase. The diffing algorithm decides what needs to change, while reconciliation decides how changes should be applied efficiently. During this process, React carefully applies only the required updates to the real DOM. Another important responsibility of reconciliation is preserving the application's current state wherever possible. If a component does not need to be recreated, React helps its existing state intact. Reconciliation also manages the life cycle of React components. When new components are introduced, React creates and inserts them into the appropriate position. If a component is no longer required, React removes it safely from the interface. Existing components continue to function normally without unnecessary interruptions. By applying updates in a structured and optimized manner, reconciliation reduces rendering time, improves application responsiveness, and allows user to interact with the application without noticeable delays. This is especially valuable in applications that display frequently changing information such as live dashboards, chat applications, stock market trackers, and online collaboration tools. In the latest versions of React, an advanced internal rendering engine called Fiber architecture was introduced. Fiber is one of the biggest improvements made to React because it allows applications to handle complex user interfaces more efficiently while maintaining a smooth and responsive user experience. Before the introduction of the Fiber, React processed the entire rendering task in one continuous operation. If the application had a large number of components to render, the browser could become temporarily busy, making the user interface feel less responsive. During this time, user interactions such as clicking a button or typing into a text box might experience a slight delay. Fiber solves this problem by breaking large rendering tasks into smaller manageable units of work. Instead of trying to complete everything at once, React processes these smaller tasks one by one. This gives React greater flexibility in deciding how and when each task should be executed. One of the most important features of Fiber is task prioritization. React understands that not every update is equally important. Some updates require an immediate response because they directly affect the user's interaction, while others can wait for a short period without affecting the user experience. For example, imagine a web application displaying a large dashboard with multiple charts and reports. At the same time, a user clicks the submit button on a form. Using Fiber, React recognizes that a button click is a high priority task because the user expects an immediate response. Therefore, React processes the button click first and postpones the less critical rendering task until the browser has available time. Another powerful capability of Fiber is interruptible rendering. Unlike earlier versions of React, Fiber allows React to temporarily pause a rendering process if a more important task arrives. After completing the high priority task, React resumes the pause to work exactly where it stopped instead of starting over from the beginning. This makes the rendering process much more efficient and prevents unnecessary computation. The fiber architecture is especially beneficial for modern applications such as social media platforms, video streaming services, online collaboration tools, e commerce websites, and data intensive dashboards where multiple updates occur simultaneously. This flow summarizes the complete life cycle of a React application. Every user action initiates a state change. React creates a new virtual DOM, compares it with the previous version, identifies the differences, performs reconciliation, updates the real DOM, and finally refreshes only the affected part of the web page. This efficient process allows React to provide high performance and a seamless user experience. Let us now summarize why React is considered one of the fastest and most efficient libraries for building modern web applications. React's performance is not based on a single feature. Instead, it is a result of several internal mechanisms working together in a coordinated manner to deliver a fast and seamless user experience. One of React's biggest strength is that it avoids unnecessary processing. Instead of repeatedly performing expensive browser operations, React follows an optimized workflow that ensures every update is carried out in the most efficient way possible. This reduces the workload on the browser and allows applications to respond quickly even when handling interfaces. Another important advantage of React is its component based architecture. Applications are divided into small, independent, and reusable components where each component performs a specific function. Since these components are modular, developers can build, test, debug, and maintain them individually without affecting the rest of the application. Reusability is another major benefit. The component created once can be used in multiple parts of the same application or even across different projects. For example, components such as navigation bars, login forms, search boxes, buttons, and footers can be reused wherever required. This reduces duplicate code, speeds up the development, and helps maintain consistency throughout the application. React is also highly scalable as applications grow from a few screens to hundreds of pages. The component based structure makes it easier to add new features, organize code, and manage large development teams. Different developers can work on separate components simultaneously, improving productivity and simplifying collaboration. In addition, React's organized architecture makes application easier to maintain. When changes or bug fixes are required, developers often need to update only the relevant component instead of searching through an entire code base. This reduces development time, minimizes errors, and simplifies future enhancements. These combined advantages make React suitable for a wide range of applications, including social media platforms, e commerce websites, online learning portals, banking systems, and many other large scale web solutions where speed, reliability, and maintainability are essential. To conclude, React develops excellent performance by combining intelligent rendering techniques with a modular development approach. Its efficient update process, organized component structure, code reusability, scalability, and ease of maintenance help enable developers to build modern web applications that are fast, reliable, and capable of handling the growing demands of today's users. So, this is the end of today's lecture on React internals. Let us summarize the important concepts that we have learned. In this session, we explored the internal working of React and understood what happens behind the scenes whenever a React application is rendered or updated. Although React provides a simple way to build user interface, it performs several intelligent operations internally to ensure that applications remain fast, efficient, and responsive. First, we understood the difference between the real DOM and the virtual DOM and learned why directly updating the real DOM repeatedly can affect the performance of large web applications. Then we saw how React uses virtual DOM as an intermediate representation to process changes efficiently before updating the browser. Next, we studied the diffing algorithm, which compares the previous and updated versions of the virtual DOM to identify exactly what has changed. This comparison enables React to avoid unnecessary processing and focus only on the portions of the interface that require modification. After that, we learned about reconciliation, the process responsible for applying those identified changes to the real DOM in an optimized manner. We also explored fiber architecture, the modern rendering engine introduced in React. Understanding these internal concepts is important because they help developers write more efficient React applications and make better design decisions while building real world projects. As your applications become larger and more complex, this knowledge will also help you to optimize performance and troubleshoot rendering issues more efficiently. These concepts explain why React applications offer faster, smoother user interactions and easier maintenance. Thank you.